All right, welcome everyone to this edition of the COMSOC video seminar. We have two fun talks scheduled. The first talk is by Klijn, who is a researcher at the Institute for Economic Analysis in Barcelona, as well as a professor at the Barcelona School of Economics, where he works on topics like assignment of indivisible objects and exchange markets. And today's talk is going to be about hedonic games and strategy-proofness. Please go ahead.
Thank you very much for the invitation and for the introduction. This is joint work with Bettina Klaus and Seckin Özbilen. Probably you know about hedonic coalition formation, but if you just want to think of an example, think of the following. So there's the dagstoel seminars in Saarland, where a group of researchers from different fields, they meet and they present their research and also try to start new research projects through on-site working groups. Now, one possible question is, how do we want to partition the participants into working groups? Okay, this is an example of an hedonic coalition formation problem, and hedonic refers simply to the fact that each agent is mostly concerned, or is basically concerned, with the members of his own coalition. In this paper we focus on good outcomes or partitions, right? So the outcomes of a hedonic coalition formation problem is a partition, and by good we refer to core stability. In general, the core for these kind of problems is empty. So what we would like to do is to look or define interesting preference domains for which these good outcomes exist. And then in the second part of the paper, we look at mechanisms, and what we would like to do is to find mechanisms that do not only give good outcomes, core stable partitions, but also mechanisms that are weakly dominant, that are strategy proof. In other words, truth telling is a weakly dominant strategy. Okay, so this is the outline of the talk. The model is extremely simple. There's a set of agents N, a finite set, subsets are called coalitions, and each agent I has preferences, and we make the assumption preferences are complete and transitive. Preferences about the possible coalitions of which he or she is a member. Okay, so the set's S for which I is a member. We do not make the assumption the preferences are strict. Okay, so typically there are indifferences. So then a hedonic game or problem is given by this pair, the set N, and the preference profile, this squiggle. And then, as I said, the outcome of a problem is a partition. So what we do is we look at what we introduce is the so-called class of friend-oriented preferences. And the easiest way to explain how this works is, I think, the following. So let's take the preference of some agent I. Then the basic assumption that we make is that if he looks at all the other agents, if he looks at any other agent, then his preferences are such that he is not indifferent between being on his own or being with the other agents. In other words, being with the other agent is either a good thing or is a bad thing, right? So that allows us to partition the set of other agents into so-called friends and a set of enemies. Okay, so maybe this terminology is not the best terminology. If you have suggestions, they are very welcome. But it will be, by just giving these names, it will be clear. You will have a clear idea of what we are referring to. Okay, so the set of friends is a set of agents J for which being with such an agent is better than being on your own, and the enemies, it's just better to be on your own than being with this other agent. Okay, simplification of the notation FI-EI. And we do not make assumptions about mutuality of friendship. Okay, then maybe this is weird, but you know, J could be a friend of I, but I could be an enemy of agent J. Now, given this basic assumption, what we do, what the real conditions are the following. So preferences are friend-oriented if the following two conditions hold. First of all, adding only an enemy is bad, right? So if I take a coalition S of which I'm a member, then adding an enemy makes the coalition worse. And then on the other hand, adding a friend together with some enemies is always a good thing. So in other words, if I start with S, I add some friend F and some set of enemies E, then the resulting coalition is better than the coalition as we started with. Okay, so these are the two assumptions we make. So let me show you an example here for agent 1. Suppose agents 2 and 3 I has friends. If we start here in the middle, agent 1 is together with his friend 2 and his enemy 4. If we add enemy 5, then we move downwards to 1, 2, 4, 5 because we are adding an enemy. And if on the other hand, if we add an additional friend together with some enemies 5, 6, then the coalition improves. Okay, so these are the two. This is the basic model. These conditions are, I would say, pretty strong. But okay, we have additional results where we try to relax these assumptions. Okay, so let me just present the results for this basic model. Okay, so then I will skip some things. So there are interesting subdomains. And then here in an example, there's 2 friends, 1 enemy. And these, in this case, there are 13 distinct preference relations that are friend-oriented. So we have slides here with examples. And there's also another condition called top responsiveness in the literature that was studied, and certain very similar results were obtained for this class of problems. But our results and the results of these researchers are logically independent. So in this Venn diagram, you can see on the left-hand side the top responsiveness, and on the right-hand side friend-oriented preferences. So what we focus on is on this part here of friend-oriented preferences. Okay, now this is a very simple example. I'm not sure if I even have to put it here, but just so that you have an idea. So 3 agents. Now, for instance, look at agent 2. Agent 2 has 2 friends, 1 and 3. And then he could say, for instance, that he prefers agent 1 to agent 3. Okay, so then we would have 1, 2 is better than 2, 3. And being with both friends is, of course, the best possible outcome, best possible coalition for this agent too. Notice, by the way, so here in this example, I forgot to mention this, you can see here there are indifferences. Every column represents a possible preference relation that is friend-oriented. So, you know, there's different types of preferences here. Okay, so now what I want to talk about is the good outcomes, which are the coarse table partitions. This is just standard definitions. So first of all, we study the strict core, and the strict core consists of partitions that are not weakly blocked. So the blocking notion here is at the top. There's no coalition S such that each agent has this F is weakly better. And for some agent J, it's strictly better. Okay, so just standard definition. Strict core, very important, it implies individual rationality and pre-optimality. And then another possibility, instead of strict core stability, one can look at core stability. So in other words, we exclude another kind of blocking, namely the blocking by collisions as such that for each agent I in S is strictly better than the the partition element in which this agent I is. Okay, so we have strict core and we have the core here. Of course, strict core is a subset of the strict core is a subset of the core because this latter blocking condition is more demanding than the other blocking condition. Okay, so strict core and core are really different notions. Here we have an example where the strict core can be a proper subset of the core. Just, you know, even I'm just giving an example for friend-oriented preferences. So even on our domain, this is the case. And the first thing is we want to know whether the strict core is really non-empty for our domain. So what we do is we construct the following graph. So we let each agent point to all her friends. So for instance, agent 2 points to agent 1 and to agent 3 and to 5 and 8. These are her friends. And then in the next step, what we do is we look at the strongly connected components. So for instance, in this graph, this directed graph, the coalition 1, 2, 3 is a strongly connected component because one can move from each of the agents to any of the other agents through a directed path. And there is no superset, a larger set that has the same property. Okay, so so then one can calculate these strongly connected components rather easily. There are algorithms to do this in linear time. So very easy. And the nice thing is that by doing this, we get a partition that turns out to be in the strict core. So in particular, the strict core is non-empty. That's the first result that we have. And then you may ask, oh, maybe it's always a unique partition, but that's not the case. Here's a very simple example, small example, where there's two strictly core stable partitions. Okay, so this is about the strict core. We also have a necessary condition for strict core stability, or in fact, a necessary condition for core stability, which says that a partition is core stable. If it's core stable, then it's either this strongly connected component partition, or it's a refinement, so where we break up some of the strongly connected components. Okay, so this is one important result that plays a key role in the proof of our main result. Since I cannot talk about this, let me go to the second part of the paper, which is about mechanisms. Okay, so mechanism is the usual thing. It's a function on a domain of preference domains, a product domain that associates with its problem or partition. And just standard mechanism is strictly core stable, individual rational operator optimal if it only assigns this type of partitions. Okay, so this is fixing preferences. Then you can define this. Now, what we are interested in is, apart from these properties, to look at strategy-proofness and group strategy-proofness. So standard strategy-proofness says simply that no agent can be strictly better off by misreporting her preferences. And then the group strategy-proofness that we look at first is the following. There is no coalition S that can improve by misstating their preferences. In other words, all agents in this coalition S weakly improve, and at least some agents strictly improves. All right. So these are just the standard notions. Now, our mechanism, the SCC, is the SCC mechanism is the mechanism that assigns to each problem this partition that we obtain with the strongly connected components. And what we can show is the following. This mechanism is strictly core stable, which is something I explained in the first theorem, but we can also show that it's a group strategy proof. Okay, so let's skip the proof. Question, okay, well, very interesting, all of this, but is this mechanism very special or not? Is it the only mechanism that satisfies the two properties? And the answer is the following. Let's think of interesting domains that are not super small. A domain that consists of one unique preference profile is of course not interesting. What we would like to look at is a domain that is larger. So for instance, a domain that we call is rich, which means that imagine we have an agent I, then for each set S, what we want to have is that there exists some preference relation for this agent I, such that this S is exactly the set of friends. Okay, so this is richness of preference domain. If all agents preferences domains are rich, then we can show that our mechanism is actually the only mechanism that is core stable and strategy proof. So our mechanism is strictly core stable and it is group strategy proof, but it turns out that in fact it's the unique mechanism that satisfies the weaker properties of core stability and strategy proofness. The two properties are logically independent. I mean, that's not really difficult to show. We have very simple examples. In fact, we slightly complicate our proof, examples. Why is that? So what we want to show, so there's two examples. One example is a mechanism that's strictly core stable but not strategy proof, and then there's a mechanism that is group strategy proof but not core stable. The mechanism that always assigns the singletons to each problem is also group strategy proof and not core stable. But we want to do something more, namely, we want to find a mechanism that on top of that is individually rational and predo-optimal. Okay, so here this is an example of that. Why did we want to do this? Well, if you think of Ma's classical characterization of the strict core for housing markets, which is a different model, he uses the property of individual rationality and predo-optimality and strategy-proofness. Now, the example that I just showed to you shows that in our characterization, core stability or strict core stability cannot be weakened to individual rationality and predo-optimality. Okay, so that's why we had the second example slightly more complicated than necessary. Now, so these were the basic results, and I have, I think, only 2 minutes left. So what we do in the rest of the paper is we try to weaken the conditions of friend-oriented preferences. So one possible thing is to do the following. So notice, if you look again at the conditions of friend-oriented preferences, E and F, then we see that these conditions are asymmetric, right? So adding only an enemy is bad. And then the second condition is not adding only a friend. It's also together with enemies. So what happens if we relax this second condition? So instead, what we demand is that adding only a friend is good. So this F bar is the new condition. Then a very simple example with 5 agents shows that the core is empty. Okay, so by making this change, making the condition symmetric, the core is empty. So then that's basically the moment that we say, okay, we will not dig further into this class of preferences. Another possibility is to switch the two conditions. In other words, now F prime is adding only a friend is good. So before it was adding only an enemy is bad. So we change enemy and friends. Adding only a friend is good. And now the second condition says adding an enemy together with friends is bad. Okay, so again, this is asymmetric, but just switching the two roles. Now you might think, okay, probably the results go through. Well, maybe surprisingly, this is not the case. Actually, the same example that I just showed for the other possible extension shows again that the core can be the core can be empty in this case. Okay, so I think I do not have any more time. Is that correct? Or
Oh, you can take another 2 minutes.
okay, thank you. So then the most interesting extension actually is the following. So now we have conditions E and F from the basic model, and we add a third condition about what we call neutrals. So let's just start from the beginning. So preferences are friend-oriented with neutrals if the set of other agents can be partitioned into 3 sets, so not just friends and enemies, but there's a third set, which we call set of neutrals. And then we have the same conditions as before, E and F, and we have the third condition N that says adding only a neutral keeps the agent indifferent. So in other words, I start with some coalition S, and I add some agent J from this set of so-called neutrals, then the agent is indifferent. Okay, so this is an extension in a different way. And interestingly, we get some more results for this extension. So first of all, the first result is that the strict core can be empty. That's the bad thing, the negative result. However, the core is non-empty in this example, but in fact, it's always non-empty. So for any friend-oriented problem with neutrals, our partition, just using the friends again, just looking at who the agents are pointing, gives us again a core stable partition. Okay, so then we ask the question, so maybe this mechanism is still group strategy proof. It turns out this is not the case. So here's an example that shows that some agent, so here this agent 2, it's a bit funny. He's, he thinks that agents 1 and 3, they are not really good, they are not really bad. He doesn't care too much whether he's part of, if they are part of his coalition. But this agent 2 then has the possibility of making someone happy. So our partition, so the strongly connected component partition, just consists of the singletons. And agent 2 now, by saying that agent 1 is his friend, can manipulate the mechanism. And now agents 1 and 2 will be together in the coalition, which for 2, he doesn't care. But obviously for agent 1, this is an improvement from being alone to being with agent 2. So this mechanism is not group strategy proof. And then the question is, wow, is this just that the mechanism is bad, or are there other mechanisms that do satisfy core stability and group strategy proofness? The answer is no. So let me skip this definition, but it's sort of the same idea as the richness condition that I presented earlier. So if we look at the domain that is rich enough, a domain of friend-oriented preferences neutrals, then we can show that there is no mechanism on that domain that is core stable and group strategy proof. Okay, so our mechanism, it's maybe not perfect, but in fact, there's no other mechanism that does the job. So question, can we weaken, so core stability we obtain with our mechanism? Maybe asking group strategy proofness is too much. Should we ask for something less, maybe strategy proofness? The answer is yes. What we in fact can do, we can do something better. Namely, we can ask something that is in between strategy proofness and group strategy proofness, namely weak group strategy proofness. So which requires that there is no coalition S that strictly improves for all its members. If we do that, so if you look at this alternative, if you use this alternative definition, then what we get is that our mechanism is core stable and weak group strategy proof. However, we do not have uniqueness. It's easy to find other mechanisms apart from our mechanism that are core stable and weak group strategy proof. Okay, so these are the results for this letter, for this third extension, and this completes the talk. So thank you very much. Let me know if you have any questions.
Thank you very much. Let's give Flip a round of applause. So thank you for a very clear talk. There have been no clarification questions during it, but we can have a discussion now. If you have a question, I guess you can start talking or raise your hand, the reaction button. Otherwise, I will start with a little bit unspecified question, which is in social choice and voting, strategy-proofness is extremely difficult to satisfy, but sort of quality guarantees like Pareto, etc., they are very easy. What about sort of this general domain? What's the harder part, the core part or the strategy-proofness part?
You mean if our preference domain? I mean,
wherever you can answer, like more generally or here, or this type of domain.
Okay, so it's hard to say in general. I mean, there's many. So I would say if you look at, so I'm not a super expert in the field of coalition formation, but from the papers that I've read and know, it's really very clear that immediately, well, very quickly, you run into problems of existence of course stable partitions, right? So, and that was our first requirement. So I understand that strategy-proofness is a very strong requirement, and I understand that many of us think maybe it's too strong a condition. But in fact, if we look at the extensions that I talked about, the first problem that occurred was in fact the existence of core stable partitions, right? So, and then we said, okay, you know, okay, the strict core can be empty. We know about models where the strict core can be empty, but then at least the core is non-empty. But even here, in this case, the core can be empty. The larger set, the core can be empty. And then in terms of proofs in this particular case, you know, this paper, I think the most difficulties that we had was with group strategy-proofness, and so that was really hard to prove, although the idea was not too difficult. And the most difficult part was the proof of the uniqueness of a mechanism that is core stable and strategy proof. I mean, that was extremely long proof.
Okay,
so
thank you.
That's all I can say. Yeah.
Reshef has put his hand up, but I'm not sure he's live. Oh, yes, he is.
Yes,
Maybe.
yes. Just an internet glitch. Everyone, sorry, I'm just I'm in the middle of moving to a new apartment, so things are a bit rocky. So the core and the group strategy forecast, they're like considering two different types of collusion behavior, and at least in this model, they can be like unrelated. So you can collude with one group in order so you can be in, together with a different group. Is there I don't know. Does it make sense to combine these and like only allow you to collude with people that you intend to join the group with or something like that?
I
know, is there any such solution concept or restriction of group manipulation or anything like that?
Well, I would say, okay, let's ask the whole group if anyone knows about this. You know, there's also other types of group strategy or strategy-proofness, right? That, for instance, in another paper we look at the group strategy-proofness notion, where that is self-enforcing in the sense that suppose we are a coalition and we think of deviating. What we do not want to have is that once we agree to deviate, that some of us have incentives to quickly change back, right? So
it's like a coalition proof. Yeah, it's called coalition proof.
So we haven't looked at that in the setting of this hedonic coalition formation, but that's an option. I don't know if there's any other kinds of strategy-proofness notions that could be interesting. I don't know if anyone knows in different contexts.
Maybe not, but Bill has his hand up.
Yeah, so the conditions you look at seem to be on the surface compatible with additive separability. And I wondered whether adding additive separability to some of your conditions that didn't lead to core stability, would that make a difference?
Okay, so let's go to let me see. So you know this here, right? So we have condition E.
That's the exact one I was thinking of. How about F bar?
Yeah, exactly. So the problem. So let me go to the example. Thank you for asking. So this is the example. So let's look at agent 1. So his friends are agents 2 and 5. Being with his 2 friends is of course the best. And then let's say he prefers 2 over 5, right? And then being on his own. The second condition, the first condition says adding an enemy is bad. So if I start with agent 1, adding an enemy, I go down. Adding a friend, I go up. And in this particular example, this is designed in such a way that all coalitions that contain at least one enemy, they are below the level of the singleton, right? So that's the particular feature of this example. I don't know which directly implies, well, because of it's 5 agents, so it's an odd number. Then you know there must be some singleton which can then seduce some other agent. Let's suppose agent 1 is alone, right? Then agent 5 is either on his own or is with agent 4, but then agent 5 is interested in being with agent 1. So agent 1 can seduce agent 5. So this shows that the core is empty. I don't know if this example.
Thank you.
Yeah.
Hey, are there any other questions? No, then let's thank Flip again. Thank you very much.
Thank you.
And we are now heading into our break. This is a 10-minute coffee break where I'll put you in random breakout rooms where if you like, you can talk to other attendees. And then we will be back at 46 past the hour. Okay, welcome back. Our second talk today is by Gerdus Benadè, who is an assistant professor at Boston University's Business School. And he is going to talk to us about just outcomes in food rescue, I believe.
Thanks, Dominic. Let me double check. Is the screen sharing?
Yes.
Perfect. All right. Hi, everyone. My name is Gerdus. So the work I'm presenting today is joint work with Aiden Optikonoglu, who's at Penn State. And we're looking at operations at a food rescue organization that operates in the US. Sorry, let me figure out why my slide is not advancing. So for some reason, when I stop sharing, it advances, and while I'm shared, it doesn't. Give me 1 second. How about now? Good. Okay. So this organization acts as a matching platform between donors and recipients, and they operate in 50 states. And very recently, their operations have sort of exploded in magnitude or scale. In 2022, nationwide, they allocated about 3 million pounds of food. And in 2023, this was more than 50 million pounds of food. And the state that we're sort of most closely looking at is Florida, which in 2023 handled about 20 million pounds of food. So a significant fraction of the US nationwide totals come from Florida. And I want to, I guess, spend most of the time today just telling you a little bit about the setting. It's been a fun project, and I think there are some interesting questions to ask here. And they'll touch a little bit on sort of theoretical and simulation results that we have here. So for everything I discuss, I'll be referring to donations below roughly £3,000. They have a separate system that handle bulk donations. And for bulk donations, you typically see recipients being willing to travel much further than for smaller donations. These systems are currently being integrated, but right now they are still separate. And for the purposes of this talk, we're only looking at the smaller donations.
Can you give examples of what is a donor and what is a recipient? What kind of?
Yes. Recipients are almost exclusively nonprofits. So you should think of something like a food pantry or a soup kitchen. Donors can be schools, it can be local stores, it can be catering companies, it can be farmers. They've had donations of like 60,000 gallons of olive oil straight from a producer. So there's quite a bit of range in like where they get their donations from and also donation sizes. Good. So the way this works, recipients, these nonprofits sign up. When they sign up, they specify a radius and they say, I'm willing to drive up to, on average, about 40 kilometers to go pick up donations. And they also indicate which categories of food they're interested in. So dairy or produce or meat. And historically, people have not been very good at specifying categories both on the donation side and the recipient side, but sort of recent pushes, I think going forward, we can expect to know category information both for donations and for recipients. In the state, they have many recipients signed up. When they are notified of a donation, they check who has this item within their pickup radius, and then they notify them through a message, either an email or a text message. Here's an example of the message that was sent a couple of weeks ago. So this is, hi Gerdus, this item is available to claim. There's a title. They say it's 4 miles away from you, and there's a description. In this case, we can get 100 individually wrapped cookies. There's an item weight, and then there's 2 links. There's a link that says claim the item, and there's a link that says view the item. So the first person to receive this message and click on the claim the item link is matched to the donor. Now, they didn't do the allocation themselves manually. They say we do the matching. So they put the donor and the recipient into touch with each other. And they say you figure out the logistics of how this gets from point A to point B yourselves. So I guess just be aware that after the time of matching, there is still a possibility that the allocation fails. And we see this in some very rare instances in the data where you have the same item being relisted 2 or 3 days later, presumably because of a failed pickup. But at least from sort of discussions with recurring donors, it seems pretty rare that this happens. So for now, I'm going to assume that once we do the match, it actually completes successfully. If you click on the view item button, you get taken to their website, and it's a different item. You have a title again, you have a description, and now we get some additional information that we didn't have before. We see the categories of this donation: protein, vegetables, and perishable. You see the address. You also see an expiration date. So I took the screenshot yesterday. So this item would have expired next Tuesday. And this expiration date typically comes from one of two places. Either it's just sort of a best by date for the food. At some point, perishable goods go off. More often, it's just the donor says, I'm willing to keep this stock around for some amount of time. If anyone picks it up by the end of the week, great. But otherwise, I need the space. I'm going to throw it out. So this expiration date is sort of the earlier of these two things that can happen. And then you see some item characteristics. You see the weight. They have some calculation for CO2 savings based on like if this were to go to a landfill instead of being consumed. And then if it's a tax deductible donation, you see some information here. For this item specifically, we see a message saying this item has already been claimed. Someone else clicked on the claim item button. We're too late to claim this. Okay, so these announcements are made. The first person to click on the link, claim it, they say they want it, they get it. And then when the next item arrives, everything resets. We check who's within the pickup radius. We send the messages. First person to say, yes, I want it, they get the item. So this is currently how their allocation system works. And historically, it's been fairly successful. So the vast majority of donations are successfully claimed before the deadline. The average claim time is about 5 hours, while the average deadline is about 200 hours. So what's that, about 8 or 9 days? Okay. And most items travel only locally, like less than 50 kilometers. So that's all good. However, because their system has this property that whoever responds fastest to a text message essentially gets the item, we do see pretty big discrepancies in how many donations different organizations receive. So on the left, I'm showing a visualization of Florida with their recipients, data over the last 5 years. And I say data from the last 5 years. Remember, the scale of their operations expanded drastically very recently. So this is sort of dominated, I guess, by 2023 data, but it technically does go back 5 years. And I guess immediately you notice there's basically one big recipient down in Miami, right? That gets essentially all of the donations in that area. Similar thing to a slightly lesser extent happens up in Jacksonville in the north. And then in the middle of the state, at least you see a more reasonable distribution of outcomes. On the right, I'm showing the Lorenz curve to measure or to visualize the inequality of this distribution. The way you should read this is, for example, at this indicated point, the bottom 60% of recipients get about 12% of donations, where sort of perfectly equal distributions would have had 60%. And if I, instead of counting the number of donations, do this in terms of the total pounds donated, then things get even worse, right? So the bottom 60% of recipients get about 5% of the total weight. And this figure is in many ways the most optimistic one that I could have drawn, because I include here only recipients that have received a donation in this time period. About 70% of the recipients in their system never receive a donation. Now, this on its own is, I guess, not necessarily worrying, right? It might be that there are 1 or 2 organizations that are just much larger than the rest. So this type of distribution might make sense in that case. So we spent some time trying to figure out like whether this is an issue, I guess. And as best as we could find out, we have very little data on the recipient organizations. They're not formal to the degree of publishing annual reports or anything. It's much more informal organizations. But from talking to folks who sort of work in the state with these organizations on a daily basis, it sounds like these recipients who try to claim these smaller donations who are able to travel only locally, they are much more homogeneous than this would suggest, or than would warrant a distribution like this. So at least from the organization side, they believe this is an issue and not sort of the type of distribution that they want to have in their system. Okay, so the the goal of our project, I guess, is somehow find a more equitable distribution of donations without breaking anything, right? We don't want to increase the fraction of unsuccessful matches, because that leads to an increase in the amount of wasted food. And coming from, I guess, previous work on online fair division problems, there's a couple of things that immediately jump out here, right? I'm used to assuming we have item values, or we can at least assume item values come from some distribution. Here we have very little agent-specific value information. We know the category, like a binary signal, are you interested in this category or not? And we know, for example, the weight of the item, but I don't know, do you like particularly 60 pounds of yogurt, right? I don't know. And one of the first things we asked them was, like, can we elicit values? Can we have some sort of bidding process? At Feeding America, there's a very neat implementation where recipient organizations get some sort of artificial currency, and then every morning they bid on up to 30 truckloads of food, and then they have a market clearing mechanism, and that takes care of the allocations. The answer we got was pretty adamant, like, no, we're not interested in eliciting values at all, and we don't think it's feasible. And maybe afterwards we can discuss like some potential reasons for that. I have hypotheses. But for now, I'm assuming we can't get access to anything more like a value than what we currently have. The second thing here is we don't really get to choose the allocation in the traditional sense, right? We don't say, here's an item, you take it. We have these announcements, and at least within this click on a claim button system, we can hope someone responds in the way that we expect. But we don't have autonomy over like selecting the allocation. As we got to talking to them more, we found out that they'd implemented a priority-based system a couple of years ago that allows you to announce an item only to a subset of the agents. And the reason they implemented was they would get donations from churches of a particular denomination, and this church would essentially say, our same church also runs a food pantry in the town over. If those folks want it, we want them to get this donation, but if they don't want it, you can give it to anyone. Okay, and this led to them implementing this priority-based system. So our idea was, let's see if we can use this idea of priority announcements and use that to delay announcements to the fastest responders, and hopefully, sort of without decreasing system-wide performance in any other way, increase the fairness in some sense of the resulting distributions. So I'm going to look at two priority-based systems. The more general one I'll call an end-stage priority list. So this is an ordering of the recipients together with announcement times. So here I have an ordering of the recipients. First I announce to the blue recipient, then the red one, then the green one. And I have announcement times. I immediately announce to blue. I announce to red after an hour if the item is still unclaimed, and then after 3 hours to the blue item. And once I announce to you, you have the option of trying to claim the item at any point up to the deadline. I can't take back an announcement. Okay. The simpler version of this is what I'll call a binary or a two-stage priority list, where there's just a set. I give priority to some set of recipients. There's a priority time. And once the priority time has passed, I announce to everybody else who doesn't yet know about the item. For an objective function, sorry, so I should say, so the announcement strategies that we consider are exactly those then defined by, that can be implemented through a priority list like this. And every priority list leads to an expected allocation. So we're sort of indirectly controlling the allocation by controlling the expected allocation. For objective function, we eventually converged on maximizing the value of the worst off agent. This is closely tied to one of the metrics that they track, that is the number of unique recipients in an area that have received donations. So our model looks something like this. We'll say that recipients have response rates that are exponentially distributed with parameters lambda. So lambda I is the parameter for the response rate of recipient I. For every item T, there is some set of agents who have this item within their pickup radius. And I'll say RT is that pickup radius. And we can also say RT captures information about the categories that you're interested in. So if you're within the radius, but you're not interested in the category of this donation, you don't appear in RT. Every item has some deadline, DT, and then we have to add a constraint that says you allocate the item with probability 1 minus alpha by time DT. If you don't add this constraint, what ends up happening is you prioritize the worst of recipients for the entire time window. And then this drastically increases the fraction of failed donations because you basically just sit around and hope someone responds and they never do. So we're going to be myopic. Whenever a donation T arrives, we're going to optimize only for this time step over our announcement strategies. So we're maximizing over X. X is the expected outcome of a priority list by time DT. The worst of agent value. And this value depends on historical allocations plus the expected allocation of the current item. And this value VI should be increasing in XI. So you can think of things like the number of items you've received, the total weight of items you've received, the fraction of your monthly demand that is fulfilled by the items you received, something like this. All of these are increasing in the XIs, and I guess our results go through for all of them. And then we have the wastage constraint that I have here that essentially says if you use a priority list, it shouldn't have more than an alpha% chance of increasing or of leading to a failed match. Good. So let me, I guess, give one example. Let's say we have 3 agents and we have different response rates, 1, 2, and 3. So 1 here is the person that is slowest, and 3 means fastest. In the current system, if you have an item without a deadline and you don't use a priority list, you immediately announce to everybody. The item is claimed with probability 1. And exponential distributions are nice because the probability that any individual agent get the item is proportional to their parameters. So the blue agent in this case gets the item with probability 1 over 6, 1 over the sum of the lambdas. So you end up with an inequitable allocation. If you allow an end-stage priority list, it's pretty easy to find announcement times, to stagger these announcements so that you end up with a perfectly balanced allocation and expectation. Okay. And this tends to be generally true if you don't have deadlines. Without deadlines, like end-stage priority lists can achieve any fractional allocations. So it turns out that by restricting ourselves to like only changing the announcement times in this way, we're not really restricting what we're able to do in terms of expected allocations. However, deadlines make things a bit harder. So for example, let's say we have a deadline of a half. I allow you to use an end-stage priority list, but I say like you must allocate the item with probability at least 95%. Then you're essentially forced not to use a priority list because of the deadline. The deadline is just too tight, and even if you immediately announce to everyone, it only leads to an allocation probability of 0.95 by time a half. You're stuck back in the unequal allocation again. Okay, so perhaps in the interest of time, let me, on the theory side, point out sort of one core insight. You might immediately think that sorting slow to fast is a good idea, and it is. And we can go a little beyond that. It turns out what's really useful is sorting by the ratio of what I'll call XIZ over your lambda, over your rate. So for any target objective function value, XIZ is the fraction that agent I needs to achieve that objective function value. So it sort of captures how far are you lagging behind. If you have very few historical allocations, then XIZ would be large. Whereas if you've gotten a lot of items historically, XIZ might be very small or even negative. Okay, so it turns out if we sort by decreasing order of these ratios, XIZ over lambda, then this is basically what we need. This gives us the right ordering for an end-stage priority list. And for a binary priority list, your set of agents that receive priority should be some prefix of this order. Good, and notice like it sort of intuitively goes the right direction, right? If 2 agents have the same rates, then this says let's prioritize the one with larger XIZ, the one that has fewer historical allocations. If 2 agents have the same historical allocations, this says let's prioritize the one that is slower, that has a smaller lambda I. it turns out you have to do binary search on this target objective function value z. But for any given target objective function z, checking if it's possible to achieve that objective function value is pretty straightforward. It's easy to compute this ordering. So subject to sort of convergence of binary search, we can find the optimal binary priority lists and end-stage priority lists in time that's polynomial in all of the parameters except how close to the optimal you want to converge. Or I guess it's log 1 over how close you get to it from the binary search. All right, so I guess I have only a small number of minutes. Let me show you the results from simulations. So we have data going back to 2017, 2018. What we do with it is we estimate response rates, and then we create simulations where for every item, we draw its donor location, its donation size, and its deadline from the historical distributions. I'm going to look at two valuation functions, the number of items you receive and the total pounds that you receive. I mentioned it also works for things like fill rate, but we don't have accurate demand information. And that's the main reason for not including it here. I'm going to compare the current system to binary and end-stage priority lists. First, in terms of the number of successful allocations, or whether or not we see an increase in the failed allocations, I ran these experiments with alpha equals 0.01, and we see all of the priority lists lead to a less than 1% increase in failed allocations. However, they do drastically increase the time it takes for an allocation to be claimed, from about 4 hours in simulations to about 80 hours. And I'll say a little bit more about that in a moment. In terms of fairness outcomes, delta objective measures the average per iteration increase in the objective function value. So when I'm tracking the number of items, the biggest improvement in objective function value I can get from any one item is 1. If someone's lagging behind, they get the item. And when everyone's perfectly equal, then the biggest increase in objective function I can get is 1 over the number of agents. Right? So here, in terms of delta objective, we see like by a factor of 20 or 25 improvements for the end-stage priority list over the current system. When I care about the total pounds that you received, the biggest possible improvement is the weight of the item. And starting from a perfectly equitable distribution, then the biggest improvement is the weight of the item divided by the number of agents here. So we see similar results here, factors of 20 or 25 improvement over the current system. If I use the Gini score to measure the overall fairness of the distribution, in absolute terms, we see improvements of about 0.2, relatively about 30%. And on the left here, I show you the Lorenz curve, the same curve as before, for the current system in blue versus the end stage and binary priority lists in orange and green. So we see significant fairness improvements of roughly 28% coming from priority lists. So if I zoom in only on those allocations, only on those donations that end up using a priority list, about 60% of them do. And when they use a priority list, these priority list ends up being pretty short, like 2 to 3 agents. And especially for the end-stage priority list, the priority time ends up being very long, like almost 300 hours. So what's happening here is, notice that on these items where I use a priority list, the average deadline is about 310 hours. So it essentially says, I'm going to give priority for as long as I possibly can, but I reserve some window of about 15 hours at the end. Because I know that once I announce to everyone, I have pretty fast responses. And this window at the end that I reserve essentially to satisfy my allocation constraint, to make sure that I still successfully allocate the item with high enough probability. Now, it's unclear for us at the moment, like whether or not this is a good thing, like system-wide. It might be that donors prefer having their donations claimed very quickly, right? And that matching someone 5 minutes before the deadline is not equivalent to matching them 5 minutes after the item is donated. So as we're right now, we're in the process of implementing this as part of their system, and hopefully we'll have a pilot up and running soon. I suspect what will end up happening is that we'll place a hard upper bound on the time, the priority time that I'm allowed to assign. We have some preliminary simulation results in the setting. We still see significant fairness improvements, but not as large as 28%, more like in the 18 to 20% range. Okay, I think I'm out of time, so let me stop here, maybe take some questions. Thank you.
Thank you very much. Let's unmute and give a round of applause. Okay, we have a few questions in the chat. I guess raise your hand if you want to say it out loud because you have more to say than you could write. But Errol asked whether the response rate of different recipients really is constant with time. Maybe it's random.
Yes, good. We don't know is the short answer. Like what I have in the historical data is only who received the item and after how long after it was announced. So at least under the assumption that if everybody has access to every item, I guess your response rate should be proportional to the fraction of historical items that you got. And we can do some estimation where we adjust for the fact that you're competing with different agents over time, like depending on where the donation is. But I don't actually have the amount of time that it took anybody to respond except for the one person who ended up getting the item. So this may vary. We are in the process of like a feature that's currently like being built is let's just track who tried to claim the item, but was unsuccessful, right? That would already help us a lot because it's also like a demand signal somehow, like more fine-grained than a general category. But I guess for modeling purposes, like we had to assume something and we assumed exponential and constant over time.
Another question. How important is the claim time? Is longer? Is it substantial? Is it harmful?
The one way we think it might affect things negative if claim time gets very long is that donors might be less likely to donate if they know this is not a quick thing that's done by the end of the day, right? If they know, sure, I can make the donation, but I should expect it to take a week, maybe this discourages donations. Beyond
so maybe
this,
it's
like,
possible.
Yeah, it's possible, but we don't have any data on this. So
maybe it's possible to do something in between, like take a slightly small delay for fast donors, but not as fast as that achieves the Rossian solution.
Yeah,
it's possible.
The simulations that I mentioned earlier, we ran a set with 24-hour limits on the priority list, which is pretty short if you think these deadlines are like 10 days or even 2 weeks, right? Potentially we'll end up going that direction just to like limit the potential negative impact of the initial trial, and then depending on what we see, we can adjust.
Cool.
Bill asked whether there's anything we can deduce from some recipient organization being slower or faster. Maybe faster organization is also just better, more efficient at distributing.
Yes, that's true. And it sort of comes back to this size issue, right? Let's say if manpower is the reason why you're slower, maybe the fact that you have more manpower means you are a larger organization, you're serving more people, and it's right that you're getting more of the allocations. The very large organizations tend not to bother with these smaller donations. They're interested in getting a truckload of food from somewhere. So I guess that's one vague reason for ruling out the fact that there might be sort of very large organizations here. The short answer is we don't know. We don't have demand information. We don't have number of meals served per month or anything from any of these recipient organizations. But the people within this organization who sort of are in daily contact, organizing the delivery, scheduling things, they have some sense of like, do these people at least have a fridge, or do they have a pickup truck that they can use, right? And based on these types of signals, for these specific set of recipients that I'm looking at, we don't think there's anyone that is an order of magnitude larger than the others. They're not identity sized, but they're within some pretty narrow range, as far as we can tell. But certainly, we've sent out several rounds of surveys. We've been phoning people trying to figure out like what's going on in the recipient organizations. Data collection is currently a little tough.
Peter, do you want to ask your question?
Oh, I can do so. I'm just curious why you have this first come immediately served scheme. You could suspend the allotment for some time and give other bidders also a chance and then have a lottery amongst the bidders. And that would give more opportunity to the slower bidders.
Yes, absolutely. Another one of our early suggestions was let's just keep bidding open until like 2 or 3 people have responded, and then amongst them select someone who's maybe been worse off historically. For whatever reason, they really like this idea of the first person to click the button gets it. And delaying announcements plus having this property that the first person to click the button gets it seems somehow more fair to folks in charge there than leaving bids open and then selecting one of potentially multiple people who have responded by some time. We're still trying to change this, but for now, I think they're pretty keen to just stick as closely as possible to the existing system, potentially with this modification of making announcement times. But what you suggest is absolutely like, if you start from scratch, like a very reasonable thing to do.
Thanks.
Have you talked to any recipients why they take so much time to answer?
No, not me personally. What we do, so I guess let me give a bit more detail on how things currently work. So if it looks like an item might go unclaimed in the current system, there is a person responsible for Florida who picks up a telephone and starts phoning people and says, hey, I have this available, do you want it? And usually this is pretty effective at getting the item placed, which sort of suggests that there's somehow knowing that someone thinks this is good for you in particular, or being nudged again, or perhaps by signaling to someone that you are given priority at least on this item, we can affect behavior, right? So one of the experiments we're thinking of setting up is like, does it make a difference if you tell someone that they're on the priority list or not, or if you reach out via multiple channels versus only one? We don't have anything conclusive yet, but this is something we're sort of considering.
Okay, thank you. Any other questions? Then thanks again to both of our speakers. Let me announce our future seminars. The next one is in March, 21st of March, when we hear from Janko Zuzana and Evi Misha. And in April, on the 18th of April, then we'll hear from Andrew Mackenzie and Wes Holiday. Thanks everyone for coming, and see you next month. Bye.
Bye-bye.